So, good afternoon all of you. I welcome you all in the third session of today's event. And these particular sessions, the title of the presentations will be Biologically Active Compounds from Chemical Probe to Drug. Without having any further delay, I again welcome Professor Stark to deliver this lecture. Thank you.
So, thank you very much for letting me speak in here. And before I start with the topic here, I have to apologize for my last blackout, and it was deeply embarrassing for me. Sorry for this. It was really the first time I have to stop a lecture in between this, so I cannot anything do more than apologize for being not accessible at this stage. Then, nevertheless, we will not continue where we have stopped there. We will continue where we have stopped on Monday, where we looked for hit to lead optimization. So now we will go a little bit more into the details or into more aspects in which this can be applied for the different drugs. Therefore, it is important to know what pharmaceutical companies really take for drug profiling in the different steps. And you see here something the companies take for the compound. They do some modeling, and they do some ranking within the different structures. With the ranking, they do this like the LE calculation, where you have calculated or where you have experimentally determined the IC50 value on your target, and you have determined the lipophilicity, for example, for the compound, and taking this into comparison. And then that's a value in which way you can compare the drug likeliness. The one is more drug likely or less drug like the other. And then you compare a set of compounds within this set of scaling ups in this way. And then you see there are some orange, some green, some red marks. And that is like in the ample, where you see red light means no-go, and green means go, and yellow or orange is something in between. And with this, you can readily oversee, even by the color coding, 10, 20 compounds directly without going into detail for each numbering on the way. Nevertheless, when you select a small number of these compounds, then you have to go into this numbering and then into the details. But the overview is sometimes much more important than to get into each detail with all of the compounds in this way. So thereby, this is some kind in which way you take the different calculations or different experimental data you really have, take into account together into this way, and that's mainly the main problem with these different structures. Just to maintain very few aspects of the Tuesday lecture. They were mostly on metabolites and metabolic structures and the different ATME properties. And here you see some compounds which have really worse ATME properties, and they really have some oxidative redox activity, some Michael acceptor properties, and so on. So these are typical compounds which are called PAINs. PAINs means pan-assay interference compounds, and they interact with everything. So you get some data, some promising IC50 value on some enzymes, but due to unspecific behavior of these compounds, not to specific structure of this. So there are different structural elements, like the hinone element here, like some tyrosine or substituted tyrosine moiety, other heterocyclic moieties. They are highly reactive in different aspects, and you should really avoid some of these aspects. So you must test your compound if it's a PAINs compound or not, if it has a redox activity or a Michael acceptor property, for example. Yeah? So Michael acceptor properties, where do we have here an example? I will show you later some example where we really want to have some Michael acceptor properties, but here I do not see it. Then we went into bioether sterism. Bioether sterism means I can make some replacement with a different structure and then get into some new compounds, maybe some new optimization for the different structures. Yeah? And here you see some cyclooxygenase 2 inhibitors, with different structures, but from the first sight you clearly see that they belong to one family. You have the aromatic moiety here, you have the heterocyclic 5-membered ring system here with some substitution, and you have here the aromatic with the sulfonamide moiety or sulfone structure there for all of the different structures. So you can easily go into some vision in which way you can clearly show which parts are replaceable by what element, or not replaceable by this element. And thereby, then you can go directly into the different aspects for the structure, and there is a just repetition in this way. This is a typical example of some me-too compounds, because they show some variations. They are new compounds by structure, but they belong to the same class of compounds. So that's clear. So they might be innovative, they might be non-obvious, but not really totally new in the different aspects. Although they have different classes, different heterocycles and so on, you see here, this is something, it's a repetition of the same pattern into this different way. And thereby pattern repetition is quite important for going into the different drugs into the way. Here you see some serotonin reuptake inhibitors, selective serotonin reuptake inhibitors, which are used as antidepressants. And you can see here also the aromatic moiety or 2 aromatic moieties. Then you have a spacer, and then you have here a secondary amine in this way. Now we go here into the other compounds, and you see also here secondary amine, secondary amine. But this is included in a ring system. This is exocyclic localized. Here the second phenyl moiety has a orientation in the tetrahydronaphthalane structure elements. Here you have 2 stereocenters in this way. Here you have also these 2 stereocenters here, but in a different orientation. And thereby you clearly see that they are more variable in the different ways, and you have a larger variation within the different structures. But when you have a close look on this, you clearly see this aromatic moiety, this secondary amine, and this aromatic moiety. They are going for the same distance. They are going in the same space within the molecule. So they have the same interaction structures. They look much more different, but once more, they are the same in the different structure. Just variations for these targets. Yeah? And what I also have to stress with the bioether sterism on one target does not mean bioether sterism on the second target. Yeah? So maybe if you look here for norepinephrine reuptake, it is different, or you have a different pattern for the different structures. Yeah? And thereby, you can change this pattern and change the orientation, and then hopefully you get new blockbuster drugs in your hands. Yeah? So that easily detectable in this way. A little bit more difficult is when you go from diazepam. I showed this benzodiazepine already with the metabolic pathway. And then you go for some other compounds like zolpidem or zolpidem, and there you also see here some heterocyclic nitrogen-containing heterocycles, but totally different to the benzodiazepine you're having here. So, and even these both heterocycles do not interfere to each other, so they have different structural elements, and they do have a basic moiety, but this is only partly comparable to this imine moiety and so on. So here you're going into a different pattern in this way, and there you go into a new class of compounds. Yeah? They do have a very similar binding properties, but these Z compounds are even more selective than the other ones. They only bind to one subgroup of this GABA A receptor element, and there are some different structure. And you must also see that there are some very slight structural variations, like we have here with the estradiol and with the testosterone. You see here in this element, everything is the same. The only difference here is that you have here a phenol compound, where you have here an alpha-beta saturated ketone compound in this area. And you clearly see or know that these are totally different hormones in this way. So even very small variations in some compound classes lead to a very strong variation in the physiological or pathophysiological effectivity with a different compound. So although many things are overlapping, sometimes one main difference can be essential to make the male hormone to a female hormone or something like this. Yeah? So that's quite important that you see these different patterns for the chemical reactivity in this way. What I do in medicinal chemistry is I always look for pattern. So I look what is repeating elements in one or the other structure element. And thereby, this pattern look must be really flexible, and you must know in which way these compounds could really react, or what is really there possible in the different ways. So I not always draw pictures like this, but there are different possibilities in which you construct the different structures, and there are variations in one or the other element. And they are not the similar compound, but changing bioesterism similar, not the same compounds. We discussed this with the biosimilars, that they're not the identical compounds in this way. And then you see that there are maybe 3 compounds which are very look-alike, and then you can vary with the different structural elements. And then it seems in which way you do these variations with the new compounds. You can make new variations within the different elements, and you can put different orientations for the different structures. Yeah? Or you can make some repetition of other elements and see if this is accepted or not. This gives you some further insight in which way you can look for the same pattern, but with variations. So there are numerous possibilities in which way you go for one or the other step. Or you can make other connection of the same elements and then see if this works better or less. It's not always necessary that you synthesize these compounds. Sometimes computational chemistry, if you have a good knowledge on the binding target, then computational chemistry can give you a great help of this and can accelerate your finding. But sometimes it's really necessary, or if you want to go further with the structure, first synthesize this compound, test the structure, and then go further. Otherwise, you may see that there was something wrong with your calculations or with your protein structure or induced fit structure. So when you go for a longer term, then it's really essential to go for the different patterns and to make some experimental data. For example, what we are doing sometimes, that we are then duplicating this pattern. You see here that the triangle is here, and then we repeat this on one or the other side in the way that we got more binding site maybe with the same structure, and thereby make some elongation of our ligands, but then have some possibility for maybe dual binding or any other things like this. So there are many possibilities in which way this can be performed if you find the correct pattern and find the similarity and find bioesterism structures. And then the possibilities for combination is quite huge. So that makes innovation, but sometimes it's like an educated guess, but the more education you have in the structure, the better your guess is in this way. So that's really the point. You have to be out of the box a little bit, but the better knowledge you have on the structure, the better out of the box you get into new structures, into new compound line for the different structures. To see what is similar or dissimilar, I do not just want to go only for chemistry. Here you see iPad or Galaxy tab. You can depend if they are similar or the same or different. So there are different possibilities. Or if you then go into history, you can see even with Star Trek or something like this, you saw something like this 20 years before, which was then later on called as a very new innovation into the different steps into the areas. Nevertheless, then you see what is new and what is not new. And you see from Steve Jobs' presentations at that time, every 2 years it was a very new thing, brand new with everything. Sometimes it's just selling, not really the only thing you go for the different structures. This innovation or pattern is not only in medicinal chemistry or in techniques, but you see here also in art. This is, you see, 2 different soups, onion and tomato soup. but they look like the same in the different area. Yeah? You have to go into the detail to see the differences in the pattern for the different structure. Yeah? And if you go then to Andy Warhol and so on, then you see he made a full picture out of the different soups of this, just being very small variations, and to see in which way the small variation then can get a bigger picture of all of the different structures in this way. Yeah? So there are quite nice exhibitions sometimes, which I looked and I saw some pattern really also in fine arts really, which can then be repeated into the different areas. So pattern repetition is quite common, and you get to be, I show that you're more open in which way you can see pattern, in which way you can see your compound. It's not only a nitrogen, maybe it's a basic center, maybe it's just a distance, maybe it's just hydrogen bonding acceptor or donor activity. Different possibility in which way you can see the different structures. Then you see here the moth and the inchworm, the wasp fly, and this genetic mimicry here and so on. So these both, they look totally different. They have the same genetic coding in this way. So they are much more the same, like these wasp here, because this wasp is just a normal wasp, and the mimicry, they have totally different genes. They just look like the same. But from the genetic things, they're totally different. So very often it's necessary to go more into detail with the different structures, and then to see in which way these things are varying. You can change these things, yeah? In which way you can change your moth or your worm maybe into a butterfly. Yeah? So that's the possibility in which way you can then go for the different structure, for the different elements, to see really in which way you're going on for the different elements and see in which way that's going. When we have developed some new interesting structures, then we always go into the optimization of these new structures. And I already explained on Monday, we are not going for quantity, we are going for quality. So by the lowest number of structural variation, we want to find the optimal compound with a structural element in this way. And here, one of these examples is a topless tree. Yeah? It is quite old, last century described in different aspects, but not very often found in medicine chemistry textbooks really so far. And I really don't know why, because I think they are quite useful, quite handy to get some optimization. So if you have your phenyl moiety in your structure, then you start, in most cases, with a chloro substitution or a methoxy or a dichloro substitution or different orientation in this way. So these are some kinds to look if it's electron releasing, electron withdrawing, if it has some lipophilic or hydrophilic interaction, just to see in which way some substance can vary, can optimize the different structure. The most important thing here is that you make the variation and directly have the possibility to test these compounds. So before the next round, you have the test results, and then you go into the next round for optimization. So if you, for example, see that the D-substituted is much better, then you go into other different D-substituted pattern in this way and not check all the other structures. If you see that the hydrophilic substitution is better than the lipophilic substitution, the chloro than the methoxy, then you go for other hydrophilic substitution and make further variations on mono or D-substitution with these structural elements in this way. So step by step, round by round, there are 3 or 4 rounds necessary to see which compounds are really then mostly essential in this way. And then you have a very good chance of getting with 10 to 20 compounds the optimal substitution pattern, where you have hundreds or a few hundred possibilities for structural variations. Yeah? And I only see it practical as a lab organizer. I do not have money for a few hundred compounds to test. I just have money for maybe 20 compounds to test there, and thereby we have to optimize for the best compound in this way, and not all things which are madeable in this way. And this is true not only for aromatic substitution, you can also take then PP interaction, different possibilities, hydrophilic, lipophilic interaction with a different substitution pattern. But you can also include then your alkyl chain. And with alkyl chain, you can see longer side-branched cyclic structures or substituted structures. So there are also possibilities in which way then you can optimize your alkyl chain in the structure. Yeah? But always be sure this is for target affinity optimization. All the structural elements you have here, they look for the possibility in which way this substitution or this change, bioesosteric replacement, leads to higher affinity. And I hope you have learned higher affinity is not everything. You have good ATME properties, good selectivity, and so on and so on. So there are many other possibilities you have to take into account with the development, but this is just if you make some optimization for your target affinity in this way. Yeah? Or target efficacy also maybe in some cases, so thereby this makes it quite clear and get into the small number of variations with a good optimization. And then you can see here, even if you go here for some cyclic compounds, you go for different cycles, yeah? Different chain lengths in which the cycle is connected, and maybe then you land once more with a phenyl group. And then you restart your substitution, then with the substitution of the phenyl group. So this end here is maybe not the end for your optimization procedures, so there are many more in these possibilities in this way. But topless tree is quite useful variation and not so often known and not so often applied. Many people think that when they use this computational chemistry approaches, then they have to prepare only one compound. Yeah? But even when you have only one compound which is better, then you have to show what is better. Is better the best, or is better just better than the other compound? So anyway, you have to synthesize a few compounds, and this makes a good way in which you can then do some optimization procedures. Yeah? But that gives us the next step from the physicochemical characterization to computational chemistry. So when we go into a structure-activity relationship or quantitative structure-activity relationship, where we measure more than only the drug lipophilicity or hydrophilicity, we are measuring the distance between the different binding areas, the difference between hydrobond acceptor, hydrobond donor effect, or even the efficacy of donor or acceptor in the different structures. So thereby different possibilities for analysis here, and thereby you should at least know in which way this is really going on for most of the structure. So in most cases we are looking for reversible ligands. I will later on show also some irreversible ligands, but I think more than 90% are reversible ligands, and reversible means that you have a reversible binding, you have an on-off phase with your structures, and thereby you must be aware in which way, which energy this reversible binding really has in the structure. Yeah? For example here, if you have the ionic relationship, it's a strong relationship on a long distance, and the carboxylic acid with the ammonia group, they are directly interacting with the structure, and that is a long distance relationship negatively to the radius in this aspect. If you then do not have it's also a very specific kind of a dipole-dipole interaction. So nothing more, but very specific into the different actions. Yeah? Then you can see that is medium distance. Yeah? Medium distance means 1 through radius by the square on this, or pi 3 in this way. So there are different possibilities in which way then you can go for the different structures. The other interaction, reversible interaction, are PP interaction or charge transfer interactions. So electron excess reacts with electron minority elements in this way, and thereby you have this electron donator acceptor complexes where, for example, phenyl can also react with an iodine. Yeah? So they can make some complexes, and then you have this interaction in the way. This is more a lipophilic interaction, and here you see a little bit more that the distance is quite important, so they have to get nearby to develop this distance in this way. And if I'm here with a distance, then we go here for dispersion forces like van der Waals actions and so on, and they have to be very near to each other, and then maybe one methylene group to another methylene group, they have an ordering in this way. My typical question with my PhD students or even with my undergrad students is here, why does this benefit of order give some energy? Because if you look for free energy, this is a getting of order. And you know from your own room where you're living, the normal way is to get into chaos, not into order. So what is here the reason why here this order is preferred? You must always be aware that we are looking here for interaction in the body, and the body is a water fluid. So normally you do have a lot of water surrounding as a water layer on this way, and there you have your water layered ordering. And when you have the ordering of the lipophilic elements, your water get liberated free, and you get more disorder than ordering in total in this way, and that is the reason why you're having things like this. And that means this dispersion forces are, at least to my mind, the most important and mostly underestimated force, because when you look on our cells mostly consist of these dispersion forces, because all of the membranes, this bilayer, they do have this structure. So without these dispersion forces, you would not be here in this structural element. So there is really, you would flow around, maybe some other being in this way, but not really in this possibility. Yeah? And then we have here some covalent binding just for interaction. And here also, I must stress that the distance is quite important in which way these compounds are really interacting. And I added here also the energy for the compounds with 120 to 450 kilojoule per mole, depending on the covalent binding properties. And for comparison also the other energy aspects here for ionic relationship, dipole reactions, or charge transfer, and so on. And you see here with dipole or charge transfer action or hydrogen bonding, you got 30 kilojoule per mole. Whereas with the ionic binding, you got only 5 kilojoule per mole. Although it's a long distance and a strong binding property, why here you get only 5 kilojoule per mole? What is the reason here? Why is you have a strong binding? Strong binding should give strong energy. What is the reason you're losing here some energy? Also, once more, the same explanation I had for the dispersion forces. We are walking always in water here. Yeah? So you have not, with the ionic structures, you do not have only one water layer, you have a number of water layers. And when these structures come together, you have to destroy these water layers and put their energy into this. And thereby, the total assumption for this structure is low, because before they can get together, you have to destroy the water layers, and then you can look for the different structure. Yeah? The water layers are much lower, much less energy with the dipole forces and so on, and with the charge transfer forces, so that could be more easily accepted into this way. So that also gives you some hints in which way your structural element must be weighed into the different structure. Yeah? Sometimes it is necessary to have some ion binding elements, but maybe you can change it a little bit to some other structures, and the non-ionic sometimes give some better properties in this way. Yeah? And there I remind on this ligand efficacy or ligand efficacy with the C log P value in this way. C log P means calculated log P value. Yeah? Calculated log P value means that you do not have to do your experimental data for this. Yeah? You can just take your computer machine and let these calculate this by increments. And you have seen my personal point is really this can give good results, but not must give good results. So you must at least check if you have to use your log D value, your experimental log D value at pH 7.4 or something like this, and then to see in which way this can be done. But nevertheless, it's a good way in which way you can describe your compounds, you can rank your compounds, and you can see which drug likeness, which compounds really have, and this can be done. So there are very nice possibilities in going for this. This is the thing of computational properties you can do with your own home computer, or even by regular calculation of the different things. When you go into modeling, then you have to use some modeling programs in this way. So modeling programs, just you have had or you will have some lectures on computational approaches or artificial intelligence, and I just want to show the basic, what they are calculating. Because in most cases, the people think, oh, we take the molecule, calculate the best orientation, and then we overlay this, and then we see what's happening there. There are lots of calculations going in between, and you must be aware which calculations have been done in this way. Otherwise, you cannot estimate the quality of these models, or in which way you follow the results you have computationally obtained. Because they are also looking only for patterns. But they are not as intelligent as you. They are stupid computers. If they have different patterns, then they always look for the same pattern. So maybe they are misleading in many ways. Yeah? So what they are doing, for example, they put on your molecule and they look for a carbonyl oxygen probe. So and then they take this three-dimensional structure and they put on all possible elements in oxygen and measure the interaction and then the binding properties between the different structures. Yeah? So they will do it as for example, carbonyl oxygen probe as an NH probe, where you have other interaction, maybe more hydrogen bonding donator possibility, carboxylate probe for ionic structures, or aromatic probe for lipophilic interaction with a different structure. These are just 4 different examples. You can make your program or give the order to your program that it takes much more interaction into account or less interaction, depending how much calculation power you have and how much interactions you really expect in this way. So thereby, you optimize these different structures in this way. And in fact, when we quite often have computational chemistry in our publications, but we do not do computational chemistry on our own. Because I have seen that there are so many computer programs are really necessary to do this, and you need 1 to 2, maybe 3 years to be familiar with the different computer programs. So we always team up here, and we take the advice of some experts, and then we work together with the expert, discuss the different things, and say why we want it like this or like that. So it's not that we say, make something and then we take it. There must be some discussion, because they are not the expert on the compounds and so on that can be done, but nevertheless they're expert on computational chemistry, and we take the expertise in our consortium and thereby help optimization of the different structures. Yeah? And then we can describe this molecule in a 3-dimensional grip with all the different interaction points. Yeah? So the 3-dimension is really something we are difficult to obtain. And in fact, nowadays, 3-dimension, ABC or XYZ, is really not always sufficient, because sometimes the on-off phase is really important. So how fast the compound is going into the binding cleft and how fast is it relieved. We are in reversible binding mode. So thereby, in the body, you have your body fluid, it takes the drug away, and then you have this interaction going on and off in this way, and thereby the dynamic calculations may be more important than the only grid interaction of a static field you're calculating. Yeah? So thereby, that's the reason why I say you need much more access to know on your activity, on your profile, on your target, on your off targets, to investigate what's really happening there in the grid and so on. Yeah? So then the computer scientists can then make your 3D interaction bases, mostly ligand-based, sometimes structure-based, depending what you really have. Yeah? Then you make your three-dimensional interaction called grid interaction, and then sometimes the people play something like a pseudoreceptor, yeah, because they're just reflecting some interacting poses, not the whole receptor, but just some important interacting poses, and then they calculate the compounds, because it's much easier, takes much less calculation power when you just have a small element and not the whole protein in this way. Yeah? Or the whole protein in a membrane, or the whole protein with interaction as a receptor dimer in the membrane, yeah? Which is now, some people calculate something like this. So thereby, you must be aware that this computation power is quite optimizing in a way, and this, what I'm showing here, is normally done always, but at a basic step only. And then you go on with some other structural elements as well. Yeah? So, and then you make the alignment of the different structures, and you see here 62 compounds, and these 62 structures are almost the same. Yeah? You see very much the same structural elements, and you see here blue is a nitrogen, red is an oxygen, and you see here this region for all of the compounds are really the same in a way. But if you look closely on this, you see some of these compounds, they have here an additional binding site. Yeah? So maybe some optimization by this binding site could be obtained. Yeah? Maybe you can leave out something here, which may be larger, big orientation, and just orientate here a little bit more into the different structures. So even if they have more or less the same binding site, in the detail, it makes much more sense to go really into the detail and to look what is different maybe for one or two compounds. Here it's only 3 compounds which are different here, and then show other possibilities. Yeah? And they demonstrate that you have here an additional binding site into this area. So be aware that there are small differences, and small differences maybe get into important ones, into the different ways. Yeah? So virtual screening is then taking a lot of compounds and screening these compounds in this way. At the moment, we are at the stage where these ultra-large screenings are performed. Ultra-large screening means 10⁹ compounds. Yeah? So more than 1 billion compounds would be screened in one screening round in the way within a few weeks. Yeah? So thereby, you must not take the whole structure. The structure had to be reduced to some elements, reduced to some binding properties in the way, reduced to some distances in this way, and then you can make this ultra-large screening for the different compounds in this way. And then when you have this ultra-large screening, you have some dropouts, which are false negative, false positive, and so on. But nevertheless, you will find a number of different compounds which then be used into more detail. And when you go into more detail, then your compound is unfolding once more. So this, if I mean this is a folded compounds, mean just folded by the information. Yeah? So we just have here aromat, carbonyl, or hydrogen bonding donator, linker, or some elements, and here, then you go for the whole molecule, and they have then better interaction, and then you make the receptor-based 3-dimensional QSNR study for the different structure, and then make a selection for the compound with the best binding mode, and then maybe you screen this compound. Would you directly prepare this compound with the best scoring factor here? When you have 9 billion compounds, or 9 billion compounds you have virtually screened, and then you go here for 20 compounds which have a good, nice scoring function. Would you go directly into synthesis of these compounds? I would go also to test the off-target properties of this compound. If I have such computing power, I do not have the computing power only for my target. I have also the same computing power for the target I do not want for the structures, and I want to check if maybe I can synthesize this compound and they're very good for the targets, but they're also very good for the off-targets in the way, and then I cannot describe anything more. So I would make more calculation on these compounds, not only on the wanted target, but also on the off-target, maybe on toxicity, and so on the drug likeness properties and so on. So molecular modeling is maybe fine and nice, but it's just one step in a long way you are going for the different structures. And then to synthesize the compounds is a proof of concept. Yeah? And that means that you can have a very nice concept and you can demonstrate all the concept, you can calculate a lot of things. Yeah? But if you do not have a proof of your concept, it's just theory. So only computational approaches is almost not enough. Yeah? So you must go into wet chemistry, into wet screening and so on. Yeah? And this was a screening where 180,000 compounds I did during my PhD thesis, or my partner did during my PhD thesis, so 20 years ago, or 30 years ago, really, in this way. And you see, this was then, at that time, a large screening, yeah? But now it's a minor screening, really, in this way. And when we go now into billion of compounds, then we got a much larger heterogeneity and so on. But you see, these compounds were then reduced to one-dimensional descriptors. There were some other descriptor taking, and then here, these were then into this grid repurposing, or getting into the grid positioning into this way. And then at the end, we ended with 61 compounds. This was really nice to have at that time, but even 61 compounds were not able to synthesize, because these 61 compounds were of large heterogeneity. It's not we changing one substituent, so you have to make almost 59 different steps for all of these synthesis routes into all of the different structures in this way. So that was not working in this way. What I have also introduced here, or we have introduced at that time, which was a little bit newer, or not, we were not the first one, but it was nice to have, that we introduced here, for example, complex interaction, or with our compound, we excluded compound with metal atoms, which always gives problems because we're working on the CNS and so on. So we excluded a lot of compounds because of the property. We excluded the hydrolipophilic compounds, so we included the physicochemical description, calculation description, just for this compound in this way. Yeah? So if they're too basic, not to go into the CNS and so on, then we went on for the different structures. So thereby, this clearly helped into the different structures in this way. This leads to my ending for the computational chemistry. And you see here, this rhodopsin model was the first model of a 7-member transmembrane-like protein. And this model here was taken up in the year 2000. Yeah? And then it took 20 years to confirm that this is really the case for other G protein coupled receptor. So there were a long time only the theoretical knowledge on a G protein-like receptor, and rhodopsin is just a G protein-like receptor, not a G protein coupled receptor. So in your eye, it's like this. And you see, and you've seen from my Warhol or other pictures there that I'm fond of fine art. And here you see a picture of René Magritte, a Belgian painter, and this picture telling this is not a pipe. Yeah? And I think this is really extraordinary for the computational model, because you clearly see that's a pipe. But it is not a pipe, it's a picture of a pipe. You do not see any pipe, it's always just a picture. And if you have a model, you do not see the real receptor, you just see the model of the receptor. So you must be aware there are some possibilities for changes and so on. So, when you make your computational chemistry, put this picture in your office to be aware that there are many other real things which are different to the picture you have of something, or to the model you have for something in this way. Yeah? Then we can go for this. Then other problems in drug development and so on. Here we're going just for adrenaline. Adrenaline, very simple natural compound, has with a catechol moiety some hydrogen bonding moiety with a hydroxyl group, also hydrogen bonding moieties, and with the secondary amine group. The secondary amine group for this biogenic amine under physiological conditions is mostly protonated. So you must have the ammonium structure, and then this ammonium structure give a ion-ion interaction with the different structures. Yeah? And then you see in which way this interacts with the adrenoreceptor and make your enhancement for energy, make your alertness and things like this. But you also see that there are two possibilities for adrenaline, and you have seen here, hopefully already, that this center here with the hydroxyl group is a stereocenter. And the hydroxyl group could be oriented in one or the other side. So thereby you have some stereochemical binding site in this way. And then I now want to know which is, I have here the model of the receptor, and I have the R-adrenaline and the S-adrenaline. And what do you assume is the natural adrenaline, the endogenous adrenaline, the R or the S form? The receptor and receptor interaction are there. I hope you clearly see that is the R form. Yeah? Because with the S form, you are missing this hydrogen bond, and this compound will have less affinity because it is missing one interaction point. Yeah? But I must also say, you see that this compound can also interact with the receptor, maybe with a slightly less affinity, reduced affinity. Maybe to other receptors it can bind better, so it has another selectivity profile. Yeah? So the other stereoisomer is not inactive, but less active here in this way. And that means why sometimes it's really important to show the difference between different stereochemical properties in this way. Yeah? So you always have this 3-point binding site, and you see here sometimes with this lettering here, sometimes it makes sense to have stereochemistry, sometimes it doesn't make sense. Yeah? So sometimes you can differentiate, sometimes it's not. So like with the bioesterism, but here you have a little bit more details in this way. Yeah? Here you see the number of racemic compounds, so with the racemic center, so not resolved into the steroid isomers, goes down and down, yeah? And the number of single enantiomers, they are slightly increasing during the time line we're having here. Yeah? But you also see that the number of achiral compounds, they are normally at a larger level, quite useful, but not as much as a stereochemistry. So at a late stage, maybe it might be necessary to introduce some stereochemistry. In your lead structure, it might be necessary to introduce some stereochemistry. In your metabolic studies, it might be useful to introduce some stereochemistry. Yeah? So we do avoid it for most of our compounds, but if it's necessary, we introduce this. Yeah? So it is with the problems. Yeah? Sometimes if you cannot avoid any problems, you add this problem and you work on this problem. Yeah? And sometimes it's just also fun to work on problems if you find some problem solution and so on. Yeah? But that's really quite helpful into this handiness and get in there into some other details in which way this can be described in a good way. So chirality is always or very often also connected to some other compounds. Other compounds, I mean natural compounds. Natural compounds, you see, and very often give some nice idea, and thereby the nature-inspired compounds, they are much more important than some de novo compounds coming out of chemical library, because you take some plants, and then there are some nice idea in which way these plants are interacting. They are used by traditional medicine in this way, and then you want to extract what compound is really the most active compound in this way. Yeah? So thereby you take this as a starting point, and my always best example is morphine, yeah? Where you have a natural compound, and 2,000 years later or something like this, they show that there's an endogenous ligand with the endorphins, yeah? And then develop also some new compound into this way. Yeah? And then we go into drug formulation and drug liberation. So when you have a very good drug but low solubility, then it gets into problem with your compound. But these problems can be solved, and there are some kind of biopharmaceutical classification system, the BCS, biopharmaceutical classification system. So there's a class 1, high solubility, high permeability. So these are the classes with no problems at all. Yeah? So they can be easily performed, and where you can easily perform some generics. Yeah? Because if these compounds do not have any problems with the drug formulation, with the absorption and so on, then the generic do not have any problems and they can be easily exchanged by each other. Class 2 gives a lower solubility, but still high permeability. So then you get some slight problems, you can overcome these problems, but that's okay with most of the different structures. Class 3 has a high solubility, low permeability, so also some problems in this way, and you have to overcome this permeability. It's because solubility is there. Maybe you have some certain drug formulations in which way then your compound is transported by patches or something like this, and then you use this good solubility, and then the solubility is then good for transport into your compartments. The worst case is you're going for class 4, low solubility, low permeability. This is always a compound where our pharmaceutical technology department is working on, because they are giving all the problems. They need some specific formulation, or they need the medicine chemist to make some optimization for the structure, to get into higher solubility, get into higher permeability into this way. Yeah? So quite often, fragment-based drug discovery within the first decade led into compounds with very large structure, and then large lipophilicity, and then low solubility and low permeability. They led to compounds in class 4 here, and then they could not develop. And then they have to de-develop their compound, make fragment deterioration and so on, and to get into compounds which are really acceptable in one or the other way. Yeah? So that's the way. So we have to go at best to class 1, and class 1 lead optimization in most cases from class 4 lead then to class 1 compounds in this way. Class 2 is just some formulation design. Class 3 is something in between, where you can sometimes by formulation or by drug optimization can do some areas. Yeah? And you see here, even class 4 compounds, hydrochlorothiazide, taxol, and furosemide, even these are compounds which are marketed, but still in special tablets or special formulations. Yeah? And if we go here for metoprolol, diltiazem, verapamil, propranolol, class 1 compounds, at least in Germany we have the classical compound, a lot of generics, because then they are sold at certain prices with the generics, and it's no problem to buy a generic because it doesn't make these problems. So this is pharmaceutical know-how really to go into one or the other way. Pharmaceutical know-how also needed when you have some compound problems. Sometimes you can make some other drug formulation. For example, here crystallization, these compounds like Gleevec, the kinase inhibitor, it needs some special kind of microcrystallization. With the microcrystallization, you put some energy in this, and then you have a higher solubility. If you make normal crystallization, then it is hardly dissolvable in any way. So microcrystallization is a form to put this compound into a blockbuster. Sometimes you do not have to change the drug, you just have to change the crystallization form, or here you have some co-crystals and thereby strongly enhance the solubility in this way. Sometimes you get into size reduction, so from crystalline form into amorphous form, and the amorphous also has some higher solubility, faster uptake in this way. Yeah? Or here, these are looking just for amorphous solid system, so some kind of special spraying system where you put your compound into an amorphous solid structural element, or you make some solubilized system, you put it into combination with some lipids and so on, and the lipid or cyclodextrin, some other cofactors, which increases their solubility in this way. Yeah? But giving something in addition to this means you have to give something more. And it's not the original drug, it's a drug formulation in combination with the other partner in this way. In the correct crystalline form, in the correct solubilized form, or whatever it could be. Yeah? But nevertheless, do not think only that the compounds could be optimized by medicine chemistry or by organic chemistry. Sometimes when you have a good compound, the drug formulation really gives you good help with all of these things. So then here you see, this is my picture for multi-component reaction. Yeah? And you have already some excellent lecture on chemical reactivity, on synthesis and so on. And multi-component reaction is where you get 3 or 4 different compounds reacted by them together and then get a couple of different ligands in this way. And then these ligands are strongly related because you always use the same starting material or related starting material. Amines, secondary amines, different structure of secondary amines. So you prepare by one synthesis maybe 3, 4, 10 different compounds in this way, and then you can test this cocktail, for example. This cocktail can be tested, and then you can see if it's active or not. If this cocktail is active, then you have to analyze the compounds after separation and to see which of these compounds in this cocktail is the most active one. So thereby, then it gives you also the possibility or the drawback that maybe some compound is an agonist and another compound is an antagonist, and they inhibit each other, so you do not see anything. Yeah? But that's false negative, which can be the case. Yeah? Something that happens, so it depends how close you're looking on. Yeah? You can look for each compound in detail, or you look sometimes on some cocktails and look what's happening there. And with a fragment library, you quite often look on cocktails. Yeah? So you give a cocktail a different library to your drug target, and then you check in which way these fragments are really binding. Instead of this library screening, where you look for the best compounds for all of the different structures. With the fragments, you then not always have the original structure, which linker you need between the different structure, which is what is really needed between the different elements. So thereby, fragment-based discovery is putting then these different things together. To my mind, the most important thing here for fragment design is fragment must be small. If you have a large fragment, it's not a fragment anymore because it's a large molecule. Because it's a small binding area, and at the end you have to put on different small binding areas to a big binding area and so on. So if you have a big fragment, you get a huge compound. A huge compound gives you huge problems with solubility, with everything that we have learned so far. Yeah? So thereby, fragments must be very small, and that is the so-called rule of 3, where the molecular weight of the structure should be below 300. The log p value or C log p value, the probability should be below 3, and hydrogen bonding donator or acceptor properties should be below 3. So small molecules, small elements that you are able at the end to put on more than 1 or 2 different fragments together. Only by that way you can then see that one fragment is then added to another and then at different position, and then you go here quite often into combinatorial chemistry, because then you can combine the different fragments into different ways and then make the new compounds into the different structures. Yeah? But please be aware, don't get into large compounds. Yeah? When you have here the fragment combination, then you go once more into optimization. You see, maybe then for the stereocenter, look for the different stereocenter. Or if you here, for example, have the isopropyl group, then you can go for the topless scheme. Is the isopropyl group really the best for the substitution or not? And then you go for other compounds. So these compounds must be optimized anyway. Or here with the aromatic moiety, or things must go into substitution for kinetics and so on. So then these compounds grew larger anyway. Yeah? So you got chloro substitution, dichloro substitution, phenyl or diphenyl elements in this way. So different possibilities in which way you grew your compound larger. That's a big problem. Stay with the small molecules and stay with these ligands here in this way. Yeah? And that is one of the reasons I explained this basic structure or the acidic structure or the amine possibilities and the lipophilicity of the different structure in so much detail. Because here with the fragment design, you have to take into account these details. In your fragments, if it's the same pKa value, does it have the same lipophilicity, does it have good solubility reason, and so on. And then you can go here for different structural elements. Yeah? And you see here, this is example, maybe a fragment that you have found, and then you can go here for different acylation status or methylation status, acylation here, or different variation. And most of these compounds here, they can be bought. Yeah? You can make them on your own, but then you have to spend, even with when you work here for a short time, then you have to spend at least, as a good experienced worker, 3 months just preparing these fragments. Yeah? And it is not only your 3 months work time, it is the solvent you're using, the analytics you have to do, the crystallization performance you have to do, the other starting materials you have to include, and taking all of this into account, in most cases, it's much cheaper and faster to buy these compounds. Yeah? Not as elegant, I must say, but really, they're, for efficacy, in most cases, it's really faster. But I have also to say that sometimes some of these compounds are sold in milligram amounts, so 10 or 20 milligrams and cost a few €100. Yeah? Then I do not allow my PhD students to buy these compounds because they are just for trials. Sometimes we can do this with other compounds and have the same information, and then we do not go for the most expensive one because they are so attractive and so nice. And here you see, to my mind, all of the spiral compounds, they look very nice and very attractive. So very, very useful compounds where you can calculate a lot of stereochemistry and orientation and so on. So that clearly helps. This clearly helps also with the computational chemistry because you have a fixed orientation with the structure. Yeah? And with fixed orientation, much less flexible in this way, much less possibilities for the different interactions. Yeah? And you see, I'm a fan of the spiral compounds, and there's really one company only focusing on spiral compounds. It's localized in Switzerland, Spirochem, and they took the slide from them, and they are very restricted in many of these things. But you can see here they take this piperazine moiety, and then they have different here spirodiamines reflecting this piperazine moiety with different steric and different orientation aspect for the different structures. Yeah? So they have developed their own, the full chemistry to 60 to 70% just on spirochemistry for different compounds in this way. Very elegant, very useful. Unfortunately, in most cases, very expensive. That's the way when you have a very special chemistry, not always can be done, then you do it. Yeah? And I must say they are really restricted in giving data away on the compounds they really have. So you really have to ask. They work on oxetans, also so oxygen-containing heterozygotes and different other things. They have expanded their way because they are quite successful in this way. But they are giving this information only on personal request. They not give everything on their website because they have learned with the very first 3 or 4 years, when they put their compound on the website, then China is preparing some of these compounds the next year and then offering for half the prices. So that's one thing they do not really want for the different structure. But so they are still quite exclusive, yeah? Exclusive by their offer, but also exclusive by their prices, I must say. Yeah? But nevertheless, you can see sometimes it's very versatile to get into these structural elements. So Spirochem, quite useful in Switzerland, localized in this way. Here you see one of these examples for fragment-based compound design, and then you see this amide for the heterozygous structure goes a little bit larger, goes with further substituent, and then goes with the structural variation with the substituents on the different structure, and then you get into this compound. Yeah? And then you see here your compound. This is just a hit with slightly above. It's just a binder. Then you go into micromolar, into 2-digit micromolar, into 1-digit micromolar, and then into submicromolar activity. And this is only one example on this, but when you look here on the ligand efficacy, you see the ligand efficacy only slightly varies with this compound. Here you see slightly variation with 0.3, and this means that this compound here is much more lipophilic than this compound. So the increase in, or the decrease in IC50 value is taken up by increase in lipophilicity. And here, with the ligand efficacy, you can clearly see there's not so much big difference between the different compounds. It is an advantage, and then at the end you have to see, does it make sense to go into this compounds, or maybe make some smaller variations here and stay with some other structural elements in the way. So thereby, this ligand efficacy is, to my mind, quite a useful point where you go here, or LELP, log p value divided to ligand efficacy, sometimes more useful because it takes more into account the lipophilicity. It depends if your ligand binding is strongly depending on lipophilicity or on distribution or things like this. So thereby these different calculation properties are there, and there are some good reviews on this. You can find with Nature Reviews, Nature Reviews in Drug Discovery, you will find several of discoveries, and you look for excellent reviews for the calculation point of these different structures. Then this kind of ligand efficacy is something I want to stress, because sometimes these terms are going inside out. And here we're looking for ligand efficacy as a term for affinity or inhibitory activity or biological activity in comparison to lipophilicity or hydrophilicity or whatever. Yeah? Here I have also another ligand efficacy for channel opening properties, and some of these ligands do partial ligand efficacy because they have partial ligand opening properties. We have the same term, but totally different meaning of this. So be aware which term is really used in which context, and here ligand efficacy is not always the calculation properties. Here is ligand efficacy, the opening probability in a channel for the different structures. So that must be clear that we do have different possibilities. And I explained to you the rule of 3, so I have also to explain the a little bit more famous rule of 5. It was determined by Chris Lipinski, who not developed this, but his company developed this, and he published this then, really. But nevertheless, it's a very famous one. And this rule of 5 is going, for a good compound, or for a bad compound, you have more than 5 hydrogen bridge donators, calculated as OH or NH, more than 2.5 or 2 times 5, namely 10 hydrobridge acceptors, also calculated as O or N, a molecular weight higher than 500, or log p value higher than 5. So when these factors are there, then you have a compound with a low probability of per-oral absorption. And this is what the rule of 5 is really describing. It's describing the possibility for pharmacokinetic properties. So if you have 1 or 2 unfavorable conditions here, then your probability sinks in the way. So you have a lower probability rate for a successful per-oral drug. But that does not mean that this drug is per se not useful. Maybe you can use another application route, IV application or something like this. So there are other possibilities. So this rule of 5 concerns per-oral application and the possibility to get new drugs or good drugs into the way. Nevertheless, most of us work in 90% of our classes, compound classes, for per-oral compounds, because it's the most convenient and most probable way for taking the drugs, and thereby this rule of 5 is really so important within the different structural elements. My last slides go for drug determination, fragment design, and in which way we can define the targets we're looking for. Here you see a compound, osimertinib, and this osimertinib is a compound which has here acrylic amide structure, and thereby have a typical Michael acceptor structure, and is an irreversible ligand. Yeah? And now you can also go here for a reverse fragmentation. Yeah? So you take this compound here, and then you make different fragments for these structures, the indole moiety, the other moieties, you stuck them with this acrylamide element, and then you look, where do these fragments bind to the receptor, to the kinase in this case, and then you look, maybe by that way I find some new binding areas which are more or less diverse within the different structures. So it's not only that you can bring together to get some basic knowledge increase, but you can also defragment some things and can also find some useful elements there. Yeah? And then there are different possibilities in which way fragmentation or defragmentation, reversible or irreversible binding are quite often used. And you see here, this GWT-NIP also cytostaticum, and has here this linker here, mostly for solubility properties. And you see the morpholine moiety has a good solubility. Otherwise, this is a very rigid aromatic structure. It would not be soluble, so it goes here with a different structure and has a good binding properties in this way. And the morpholine moiety you see here does not really contribute too much to the binding in this way, but contribute to the error. And then you can hear very similar binding properties. Here also solubility factors. And here you can see a variation of the acrylamide structure with the amine element from the morpholine or from other structural element, also for hydrophilicity, lipophilicity, but here with these Michael acceptor properties for irreversible binding properties. So you can change the property of your binding elements by adding some of these other fragments into this way. Also, I think it's a bioisosteric approach, although you can clearly see that's not bioisosteric, because this is reversible and this is irreversible. So it could not be bioisosteric, but the binding properties are the same, and then you can bind to some cysteines in most cases here, and the cysteine then bind here to the different actions. So if you have knowledge of your binding properties and you have a cysteine there, this clearly reacts with some Michael acceptor things, and then you can go here for the different structures. So, and this is really done with a lot of different newer compounds for cancer development, because you want to hit hard and fast with your cancer treatment, and that is a possibility with irreversible ligands. You may have a slightly higher toxicity, but you have toxicity with most cancer treatments at all. So the protection of the patient and the hard hitting is really the favorable way to treat the patient. Yeah? And you see with some other diseases, this irreversible approach would not be as effective as it is. The acrylamide is not the only thing in which you get Michael acceptor properties. Sometimes here you see a cyano moiety could be already sufficient in this way. The cyano moiety binds also to the cysteamine moiety. It's a binding moiety where the binding for the cysteine is covalently done, but it is reversible. It's a covalent reversible binding structure, so it binds a little bit harder, a little bit tighter in this way, but then it's still reversible because of the cyano functionality. So the possibility for structural variations are also here multiple possibilities, and thereby you must know in which way they are interacting, where you have some reactive elements in your receptor element, your target element. Here it's a kinase in this way, and then you can go for the structure. Then you have to detect this. I promise these are my last slides for today here. And then here you have to detect which is really your target and where is your target bound. Very important thing, I believe. And sometimes, especially when you work on natural compounds, yeah? These natural compounds give health, yeah? But health maybe less neurodegeneration. Less neurodegeneration on which neurons, on which target, and so on. Yeah? And then you have to find, for example, one active ingredient, and then you modify this active ingredient. And here, you see here, this ingredient here is a polyethylene glycol flag here. And then with this polyethylene glycol flag, this compound binds to your receptor or to your target, and then you can extract your target bound to this ligand here. Or what I find even more intriguing, photoaffinity labeling. This aziridine element here is highly photoreactive, so you interact your target, your compound, with your compound. You stay this for a while, and then you make some photoactivation, you make some kind of bleaching, and this moiety here is highly reactive, and then you make some covalent bound to your receptor, to your target, and then by protein analysis, mostly LCMS, then you can see where this compound has been bound. Yeah? So that's quite effective in different ways. Yeah? Activity profiling with this nitroxide here, so you can see which cell line is activated or not. Or thermal stability. For example, this compound here binds to the receptor, and by the binding of the receptor, it stabilizes its melting point, or its melting point goes much higher in this way. And then you put this to the protein, then you increase the temperature, all other proteins are destroyed, and then you can isolate your protein, which is not destroyed in this melting process. Yeah? So thereby different stability, or here, this is more or less the same. It's called for proteolytic stability. So if this compound is bound, then the receptor or the target, the protein, is changing its conformation. It's not a substrate for a proteasome deterioration, and then your protein stays the same when it binds this receptor. So this was just a rough overview on at least 5 different points of action in which you can de-orphanize your target. You can show your target. You need a useful compound, you need the position where your compound could be modified, and you need a good method in which this modification really gives this thing. Yeah? In most cases, many of the organic chemists, they prefer this photocatalysis in this way and these different structure, because then you can put everything into the compound in this way. Yeah? And then you can modify the compound in a different way, because here you have to be mostly a biochemist to work on thermal stability, to have enough protein, and to go for these different areas. So thereby, this is really quite useful. Yeah? There are also some other screening systems, resistance screening for antibiotics, chemogenetic profiling for other things. So there are different possibilities in which ways you can do these different things. Yeah? Many of these readouts strongly depends on the assays you really have. So what is the basis of your assay? Do you have, for example, X-ray crystallography, and you have the picture where your compound is binding in the protein? Or do you have cryo electron microscopy? Also, you have the direct picture where your compound is binding to the protein. This is the most convenient one, but also the most rare ones you really have. You get very rarely into the different. Yeah? Then the most often are competition experiments. Competition experiments means displacement at the target, displacement at the receptor. But therefore, you need another compound which has the same binding mode, and that must be displaced. And you must have this displacement partner in a visible form, mostly fluorescence or radioactive form, and then you can easily look for the displacement. And then you have autosteric displacement on the same binding site. Slightly allosteric, allosteric site, by the way. NMR study, site-directed mutagenesis, where you modify your protein with some amino acid. This covalent or photoaffinity labeling, where you look for the binding of your structure to the protein, and then you have a new protein, and then you have a new mass for your protein in this way. Yeah. Deuterium, hydrogen deuterium exchange also is connected to mass spectrometry, because your compound is deuterated, and then you give your deuterated compound to your target, then it interacts with the target, there's a slight exchange with the hydrogen with the deuterium, and then your target got some deuteration on the binding site. And then by mass spectrometry, you can detect this binding site also with a different site. Yeah? Stability profiling I also mentioned, and the computation approaches as a theoretical approach to go for this different structure. Yeah? Then I just want, here there's this chemical probe thing. Yeah? Chemical probe means that you have a very good, nice compound, and this compound in most cases works selective, but it is not really taken as a drug. And chemical probe really depends. Is it a chemical probe, what we have discussed yesterday, on the target? Yeah? Is it a good chemical, or is it good, the day before yesterday, is it a good chemical probe for the cellular system? Does it penetrate the cell? Is it a good chemical probe for tissues? Is it a good chemical probe for animal models, or for dog models, or monkey models, or for human use? Yeah? That's different variation of the same chemical probe, and the better the probe, the better it can be used as a selective target for everything, but it must not be a drug. Maybe the chemical probe is very useful, maybe it's toxic, but then you can use it in human tissues, for example, that have been extracted before, and then can determine some of these things. So this kind of chemical probe is quite useful, and there is a website, Chemical Probe, where I'm in the editorial board of this structure, where you can develop some probe. You have the publication of this probe, and then you can send this chemical probe to this organization. It's localized mostly in Frankfurt, Germany, and then other reviewers will evaluate if this is the correct terming for the chemical probe, and if your chemical probe is good in which concentration, in which disease model, in which cell models, in which target models, and so on. So where does it have selectivity and useful approachings in the different possibilities. Yeah? And with this, I would stop today. I think that's I think useful for these things. I can go easily further with the chemical probes, but I think due to time, and you already had some interesting lectures today, it would be good for now. Thank you.
So thank you, Professor Stark, for this nice lecture. Please join me in thanking him for this excellent topic, how lucidly he has presented. So now this session is open for some questions, answers, maybe some discussions. So any questions you can ask? Any questions from, see, you should be interacting, otherwise, you know, last day you have to appear in the exam. Now if you are not clarifying your doubts, then you can understand what will be happening. If you are not understanding this topic, the questions will be coming from here. So you are not understanding the things that has to be clarified.
You can also ask questions from yesterday morning for the
exactly.
plasma properties, if it's necessary.
Yes. So please ask question and clarify the doubts, or if you want to know more about it.
There I was really short with my explanations.
And I told there will be award for asking question, interacting also. No questions?
Do we have some questions from the online area?
No, they are not asking actually. So,
okay.
So that yeah.
Good afternoon, sir.
They can send emails from the online person.
Sir, I don't mean what is doping of ligands?
The topic of ligands?
Doping of ligands.
Doping of ligands.
Doping. Doping of ligands means, in many cases, it's the variation that you're going from hydrogen to deuterium. It's doping. In most cases meant. I'm not sure if you mean this directly with the doping.
So, doping of ligands into receptors.
Docking you mean, docking is it, yeah. Docking means that your receptor has different conformations, yeah? So it can be flexible in this way. The same is true for your ligands. And then you have to find the correct pose for your receptor, where it's activated, for example, and in which way then your ligand is binding to this receptor at which area into this area. And then these then have to fit together, and this means docking together. So the docking behavior is then that two partners really have some different interaction areas, and these different interaction areas then fit together, and the better they are fitting together, the better the binding affinity, and the better their general affinity they have. By computational chemistry, you can calculate the binding affinity. So what I just said, the different aspects of reversible binding in the structure, so in which way they are going there. And that strongly depends in which way you localize your ligand. So if you localize like this, or like this, or like this, so you have the binding cleft, and then it strongly depends on the way. The main difficulty here is that you have your receptor maybe in an agonist or an antagonist state. So both states are really active, inactive or fully active, but they have different binding areas. They have, yeah? Then you can calculate for both of this. The same is true for your ligand. Your ligand has a most stable conformation. Yeah? So, and most stable conformation not as crystal, but most stable conformation in water solubility, mostly at pH 7.4. Yeah? And then this interacts here, and then you have to see what I explained with the receptor-ligand interaction. Then sometimes you have an induced fit. So you have a binding here. The binding here changes the conformation of the receptor, and then the ligand changes, and at the end, both of them have changed their conformation, but they bind very tightly together. And that's very difficult to calculate because you have strong calculation power to measure this kind of flexibility. And the more power you input, the better your results with this.
Thank you.
Okay.
Any other questions from this side?
Sir, could you please clarify what is pains and the brink alerts, and how much alerts are allowed, or there should not be any alerts in our compound?
Yeah. You mean with the rule of 5,
Yes.
for example? Yeah. With the rule of 5, every violation can be allowed. Yeah? It's just a rule of thumb, yeah? And there are some compounds that describe which are violating all 4. These are the rule of 5, only 4 rules. I must be aware, yeah? For 4 rules, and they are just multiple of 5 or of 5. That's why they call rule of 5. And you can really deteriorate all 4 of them and still have a compound which went into market. The probability that it went into market is maybe 5%. If you have a compound which is not deteriorating all 4, it increases to 10, maybe 20. But if it's not deteriorating any of the 4, its probability is more than 50% for these factors described there. So it is just that there are some factors in which way these compounds could be described, and the probability factor is there, but this is just statistics. And with the statistics, you always find a few examples which are outliers of the statistics. And you have seen even with the biopharmaceutical classification systems, even some compounds in class 4 went into market. They're very awful physicochemical properties, but still acceptable under certain conditions. So that's the difficulty we are working on. There are many examples in which way you must not really directly follow, but your chances of getting a good compound, it's much better if you follow this directions. And it's very difficult to follow this direction when you go for fragment-based design, because with a fragment-based design, you have 2 or 3 fragments, and you have to put 3 fragments at least together. So, and if you saw one fragment has a molecular weight below 300, if you have 3 fragments together, you have a molecular weight of about 900 already. That's the problem when the 2 fragments may be not enough, and then sure. That's a regular problem with fragment-based design, that you're going into good compounds or good chemical probes, but not really to good drugs because of the missing rule of 5 by Lipinski. So in most cases, you have to put different things together. So that's why I put so much information at the beginning of the basics on this, and the basics then really are really essential to understand at the end the complexity for the medicine chemistry. So in general, medicine chemistry is very, very nice and very, very simple. Yeah? Simple rules, simple effectivity, small molecules, and so on. Yeah? Hopefully simple chemistry, I'm not sure, but at the end, many structural variations lead to more complex chemistry when you go for one special compound way. But we prefer to have simple chemistry at the very first beginning, and then have simple chemistry for building up structure activity relationship. And when we go in our best compound, then we have to optimize the basic chemistry once more. So then we go into much more chemical aspects than we have had before, because before that we were just interested in getting the compound fast. Yeah? And maybe...
Thank you, sir.
Yeah. Maybe the main difference here in medicine chemistry is you have to get a compound for screening. Yeah? Without getting the compound for screening, you have no information in medicine chemistry. Having assumed that it's a nice compound or something like this is just an assumption. Yeah? So medicine chemistry is not on the nice way. It's to have the final compound for screening. And it must not really lead to a drug. I will show tomorrow that we also have some compounds which are good chemical probes, highly used chemical probes. The failure of us at the very beginning, at the end, a very nice chemical probe for usability.
Hello, good afternoon, sir. Sir, how the target cell tissue in the body, that's where it's be working.
For the target cell, you mean?
The drug target, detect the target molecule or
Yeah.
tissue in the body, and working principle, it's...
For drug target identification, or the target identification is, to my mind, very important. When, for example, aspirin was introduced into the market more than 100 years ago, nobody knows in which way it works, or it just works like this. Yeah? I think nowadays you would not be able to introduce aspirin into the market anymore because of the stomach toxicity. So it would not go into clinical trials anyway, because there were too much toxicity included in the way. We take now the risk-benefit ratio for this compound, but we are going on. Then it took 80 years, I think, to develop the target, to find the target for cyclooxygenase. The cyclooxygenase is really the target. Yeah? That means there must be a large input in biochemistry, in the signaling mechanism, and all the understanding. And still there are some compounds, some traditional medicine compounds, where we do not know the targets. They are effective, but we're not really clear what is the real target. Or I think paracetamol is something like this. It has very low COX inhibition, moderate COX inhibition, but it goes better into the brain. We do not really know what is the target there. And then it would be important really to see where it binds and where it does not bind. And in which way you can then identify this target. That is or for antibiotics. Yeah? You can have very good bacteria killing systems, but if you do not identify the target and see that the target is only in bacteria and not in humans, they're not allowed to apply this antibiotic, this cytotoxic compound, into humans, because you have not shown that it is non-toxic for humans. And thereby you must show that the target is only there in bacteria and not in humans. The problem here is then in which way you can detect this compound. Compounds that sometimes kill some cells have multiple factors in this. And that was one of the reasons for this photoaffinity labeling, where you have your compound, and then you add some photoaffinity label to your compound. And then you include your active compound into the bacteria, and then make the light instruction. You have a covalent binding of the protein, hopefully. Yeah? Then you make some washing, then you make a reanalysis of all the proteins, and then you see in which way this is protein coupled. So it must be you have to analyze all the proteins before labeling and after labeling to see the difference, which protein is really been. Yeah? So it's kind of diffraction mass spectrometry. and then you find something like this. But I believe, my personal point of view, that's quite difficult in many cases. Yeah? Also, you can make some affinity screening. For example, you can label your compound with biotin, yeah? And then you have a avidine-packed column, and the biotin-avidine interaction is very, very covalently, or covalently like, and then your compound is binding to this column by the biotin-avidine interaction, and then you make some cell lysate through the column, and your target, because of the higher affinity to your compound, would be stuck on the column where the other will be eluted. And at the end, then you elute your target with the structure. But that's a lot of biochemistry to find the protein within the correct pH value, that they are not deuterated, and to eluate all the other compounds without eluating your other reversible binding mode in this way. So there are a lot of things to, a lot of input which had to be done to be successful there. And I know at least 50 studies who tried, and I know 5 studies who succeeded. Just a little bit information on the success rate for these things. Yeah? Quite difficult.
Yeah. So, any other questions? Yeah.
Sir, my question is, what is the difference between amorphous solid and amorphous solid dispersion?
Yeah. That's a pharmaceutical technology question. The amorphous are really solid material, and the amorphous liquid solid, they are, the preparation is in another material, and then it is a so-called solid liquid. Yeah? It is the molecular behavior is not like a solid. The molecular behavior is that it can move between the different molecules like a liquid, but if you weight this compound and structure this compound, it is solid. It's a special pharmaceutical technology formulation which can be done by some co-spraying structure. So you put some energy on this, and then you liberate the fluid, water, or some other solvent from this, and then it's stuck into a highly amorphous structure, but in connection to the other elements. And this means solid liquid. Yeah? It's not a new phase, but it's a pharmaceutical technology formulation structure, and this gives the possibility to put energy into your compound, and this energy helps to get easier into solution. So all of these things you see with microcrystalline, with amorphous structure, you always put a little bit more energy into the molecule, into its solid state, and then it's easier for solubility. So it's not easier dissoluted, but solubility is increased because this state has a higher energy. The drawback of these pharmaceutical formulation is the more energy you put inside, the easier they form the more stable structure. So they are less stable on the long range. And this amorphous liquid solids, I think they are stable for about 1 year and not really longer. So for tablets and so on, it's not possible. Mostly this is used in some other formulations. But it's a very, very specific form, and also I'm also not the expert on this, but we do have expert on this formulation technique.
Any more questions?
Sir, in molecular docking, we get the binding energy according to different poses of ligands. but sometimes the first pose having maximum binding energy, but the pose is not superimposable with the co-crystallized ligand.
Yep.
And suppose pose third or fourth having less binding energy but superimposable with co-crystallized ligand.
Yep.
So in what case, which score will be considered?
Yeah. When you make some superimposing, some co-crystallization, or take some crystals or even co-crystals, X-ray studies and so on, then, as you said, you work on the crystals, which is not true in the membrane, because then you have the liquid protein in this way, in the liquid area solubilized protein. So it is just an artifact that you are preparing for X-ray studies, and it is not the exact structure. It is the exact structure that you have determined in this cubist crystal. Yeah? But these cubist crystals are then really there. They're not really there in the membrane. So your model is not really, even if it's based on the X-ray structure or cryo-EM or so on, they are on one stage. They are frozen on one stage. Yeah? There are some possibilities, especially for GPCRs and others, that there are some agonist-antagonist binding. There are some binding with G protein or without G protein. There are some binding with nanoparticles or without nanoparticles. And there are some binding with site-directed mutagenesis or not. So you have a much broader picture in which way the protein is behaving, is changing its structure by changing different parameters. And then at the end, you have to bring up your model to put in these behavior for mobility within the protein, and then your mobile ligand has to bind within this mobile protein into a good structure. The more you stick to one crystal structure, the more you stick to one description of the mobility, and not all of them. And that's the reason why many of these studies just for binding calculations fail, because they are not having the whole picture. This is my pipe, yeah, where you're looking. It looks like the structure, it looks like everything, but it's not the pipe by itself, because it's not showing the flexibility. And with the proteins, you really have the flexibility. With the protein in the membrane, you have the flexibility. To add maybe some further complexity in this way, it was shown that some receptors makes a dimerization, some homodimerization or heterodimerization with some others, so they change their interaction points, and that there are some kind of lipid rafts sometimes. Lipid rafts mean that the lipid composition of the membrane changes, and thereby changes the flexibility of the proteins, and some proteins have a higher concentration in raft in some specific lipid raft in this way. So if you take the general lipid bilayer, it's maybe not appropriate for all of the G protein coupled receptor or transmembrane receptors. Maybe some have to, in the surrounding area, surrounding lipophilic area, had to take something else, which is not fully described. And therefore, the X-ray studies or things like this, you have to use very specific lipophilic compounds to make the crystallization happens. Yeah? I met Brian Kubilka and Ray Stevens, who prepared the first X-ray studies of the beta-2 receptor, and Kubilka got the Nobel Prize for this, and they said they made some mutagenesis study on the receptor to make it more thermostable, yeah, that the X-ray would be studied. And then Ray Stevens made a huge number of evaluations for different lipophilic elements in which way this could be crystallized. And at the end, what was successful, not the rational approach to take the point mutagenesis, the rational approach to take some clear proteins on this way for crystallization. And at the end, they had to try about 3,000 different methods for crystallization to be successful with one. Different magnesium, sodium, different elements to be added and so on. And that was only because some micro titration, and then they could do this. If they had to do it by the traditional method, where you take a larger amount, then a few gram of the protein had to be there, and so a few hundred milligram were successful for this. But you see, new techniques, new evaluations, and then you get your Nobel Prize, sooner or later.
Thank you, sir.
Any more questions?
What are the effects of conformational changes such as racemic and enantiomeric molecule on affinities of receptor and subreceptors?
You mean when it's necessary or not necessary to make the resolvement, or yeah. When we have two or more stereocenters, then in most cases we try to make some resolvement because our heterogeneity of the compound are really too much. When we have one compound with one stereocenter as a racemic compound and it's potent, then we take it as it is. Because when it's potent, maybe it has 10 nanomolar, yeah, which for mini compound is potent. And then you make the selection, then your most active compound could be at best 5 nanomolar. Because it halves, if the other stereo compound is fully inactive, yeah, then it could be only 5 nanomolar because we are just measuring affinity, not efficacy. So if the other compound is fully ineffective, non-affine, you can only half the concentration, and then it's from 10 to 5 nanomolar. That's okay, but that's not really essential for us. When we have a compound which is 1 nanomolar, yeah, and then we go to 0.5 nanomolar, then maybe that could be considered to be separated into the different enantiomers, because then it is really making a bigger difference to get into this verification. And when we have some with 100 and so on, it doesn't matter because we have a lot of compounds which do not have any stereocenter and they're active in this concentration range. So only if we can have some new added information, then we make the separation of the enantiomers. Yeah? And in fact, in most cases, we try to make the separation by synthesis. So we try to synthesize the enantiomeric form. It's a more elegant, instead of making the racemic separation. That's
Resolutions.
yeah.
Anything else?
Chirosynthesis.
Yes. We talked about it. Today morning we talked
Yeah.
about
Yeah.
L-dopers. Yeah. No? You should ask question.
There were some
It's
questions.
making some noise. Yeah, any other questions? No? Okay, then if there is no more question, please join me again thanking him for this wonderful lecture and answering the questions. So now we'll be closing today's event, today's session. So tomorrow it will be starting around 10:30, as if like today. So tomorrow you please bring the laptop for the hands-on training. And as well as like maybe in the 7th, we'll conduct the exam in the morning time before the lectures. Okay, so be prepared for that. And one more announcement, please be on time. Today also, though we have delayed half an hour for your convenience, but you came again after 10:30. That is not, yeah, like something not allowed for us because it distracts the speakers. They'll be having in the morning with full enthusiasm and all. So you should maintain the time, at least the starting sessions, and you should be attending all the sessions consecutively. Okay. So that's a request from my side. Okay then. Thank you very much. Bye.